Hey everyone, welcome back to another explainer. Today we're diving head first into the incredibly complex, yet honestly super fascinating world of modern AI infrastructure. Specifically, we're looking at Supermicro's SuperCloud Composer, you'll hear me call it SCC, specifically release 3.1.00 from March 2026. We're going to figure out exactly how to unify the telemetry of a deeply heterogeneous data center.
So let's kick things off with a pretty massive question. How on earth do you actually monitor a data center that's running AMD, Nvidia, and Intel Gaudi accelerators all under the exact same roof? I mean, if you're an IT admin or a DevOps engineer, you already know this is a literal headache. You're dealing with different drivers, totally different metrics, different software stacks, and, let's be real, usually different support tickets. So how do we actually turn all that chaos into clarity?
Quick look at our roadmap for today. We'll start with unified AI hardware monitoring, then jump into the AMD SMI exporter setup, followed by the Nvidia DCGM exporter. After that, we'll configure the Prometheus server, and finally wrap up with the Gaudi 3 exporter setup.
All right, let's dive into Section 1, Unified AI Hardware Monitoring, which is really the hub of the data center. Think of this setup like a giant wheel. On the outer edge, we've got our spokes. These are the individual compute hosts completely packed with GPUs. Now, each of these hosts runs a little piece of software called an exporter, which collects data. Right in the middle, we have our hub. This is a Prometheus container that's constantly pulling or scraping those metrics from the edges. And finally, all that data gets pushed directly to SuperCloud Composer via an HTTP API. The result? A beautiful, single pane of glass for your entire infrastructure. Now, to really grasp how this all works, we've got to understand that hub. Prometheus is basically the central nervous system of this whole operation. It's an open-source systems monitoring toolkit, and its main job is to just constantly pull in performance measurements, what we call time series data, from those individual hardware endpoints we just talked about. It acts as the ultimate universal translator for all our mismatched hardware.
Moving right along to Section 2, the AMD SMI exporter setup, where we'll look at integrating ROCm.
Okay, so getting the AMD nodes set up on Ubuntu 22.04.5 actually follows a really logical sequence. We don't need to get bogged down in the dense terminal commands here. Just think of it as a simple three-step workflow. First up, you lay the groundwork by installing the ROCm drivers and clearing out any old libraries. Second, you prep your environment. That means installing the AMD System Management Interface Library and Golang, which you're going to need to compile the software. And finally, step 3, you just clone the exporter repository, build it with Go, and fire up the service.
The really crucial takeaway here is how this exporter actually lives on the machine once it's built. It runs natively as a systemd service. Using standard systemctl commands, you just enable it, start it, and it sits there quietly in the background like a totally reliable system daemon, constantly exposing all those juicy metrics to port 2021. Okay, let's shift gears to Section 3, Nvidia DCGM exporter setup. We're talking CUDA and telemetry now.
So the Nvidia integration has a very similar rhythm to AMD, but it uses a totally different toolset, and this time we're deploying on Ubuntu Server 2404. Step 1, you get those proprietary CUDA toolkit and drivers up and running. Next, you install NVIDIA's Data Center GPU Manager, usually just called DCGM, along with Golang. And for the final step, you compile the DCGM exporter straight from its source repository, generate your config files, and launch the whole thing.
Now, why go through all this trouble? Well, the sheer depth of the telemetry you unlock with DCGM is absolutely incredible. You're not just checking if the GPU is simply on. No, you are tracking streaming multiprocessor clock speeds down to the megahertz, exact power draw in watts, PCI transmission bytes, and incredibly granular utilization percentages for things like memory copy, encoders, and decoders. This level of detail is absolutely vital when you're trying to diagnose bottlenecks or just maintain the health of some incredibly expensive hardware.
Let's keep rolling. Section 4, configuring the Prometheus server, or how we actually centralize all this data.
Setting up the Prometheus hub itself is a pretty straightforward administrative task. You kick things off by creating a dedicated system user and some secure directories, just to make sure the service is properly sandboxed. Then, you download and extract the binaries. For this specific March 2026 SCC release, we're using Prometheus version 3.5.0. After moving those binaries into place, you configure the core file, which is prometheus.yml, and finally, set it up to run continuously as its own systemd service.
Taking a peek inside the global configuration for that Prometheus YAML file, there's something really cool to notice. The scrape interval is set to 15 seconds. That means every 15 seconds, Prometheus is reaching out to every single hardware node in your entire data center and pulling fresh telemetry. You are getting near real-time insights into exactly what your AI workloads are doing.
And this right here is how we actually connect the spokes to the hub. Further down in that exact same config file, we add our specific target servers. You can see the configuration blocks for our Nvidia nodes pointing directly to their specific IP addresses and appending port 9400. If you remember, that's exactly where the DCGM exporter we built earlier is broadcasting. It's an incredibly elegant and highly scalable way to handle things.
Once you've restarted the service and opened up your firewall on port 9090, boom, you unlock the Prometheus web interface. Admins can just point a web browser straight to the Prometheus server's IP address and instantly pull up a graphical dashboard. This is a lifesaver because it lets you immediately verify that data is actively flowing from the compute nodes right into your hub long before it ever gets passed along to SuperCloud Composer.
All right, moving into our final hardware integration, Section 5, Gaudi 3 Exporter Setup, and we're looking at a containerized deployment here.
Now, this brings us to a completely different kind of deployment narrative. Let's draw a really clear contrast for a second. While our AMD and Nvidia setups required us to manually compile code with Golang and create traditional native OS system daemons via system control, the Gaudi 3 environment opts for a much more modern approach. The Gaudi 3 exporter is actually deployed as a pre-packaged, completely isolated Docker container.
Because it relies on Docker, this workflow is just incredibly streamlined. You run the Habbanala Labs installer script to get your base drivers locked in. Then, you literally just execute a Docker run command that pulls the metric exporter image directly from Habana Labs' vault. And just like that, your metrics are live. Verifying them is as simple as checking port 41611. It's crazy how fast you can spin this up.
Section 6, Unified Telemetry, and how we're future-proofing the data center.
Let's quickly recap the absolute most crucial takeaways from all these Supermicro integration guides. By using Prometheus as our central bridge, SuperCloud Composer literally transforms a fragmented, overly complex hardware ecosystem into one unified, single pane of glass. Honestly, it doesn't even matter if a rack is running AMD ROCm, Nvidia CUDA, or Intel Habana Labs drivers. All that telemetry gets standardized into time series metrics, which gives you granular, actually actionable insights across an architecture that can scale massively. So I want to leave you with one final thought to chew on. As AI models become increasingly complex and data centers continue to rapidly diversify their hardware in 2026, you really have to ask yourself, is your infrastructure's telemetry unified enough to keep up? Because as we've seen today, the tools to bridge those massive hardware gaps, they're already right here. Thanks so much for joining me on this explainer, and I'll catch you in the next one.